Uh, Good afternoon, everyone. My name is Oyo. In this presentation, we aim to analyze how many energies could be recycled for electrical vehicles in a trip using passively collected trajectory data. As we all know, global warming is a serious problem in the world, and the emissions from the transport sector take up about 25% of CO2 emissions. This share is still rising recently. Compared to the conventional internal combustion engine vehicles, the EVs is replace the fossil fuels with electrical power, which could be obtained from the renewable energy resources. So it is a cleaner car. Another advantage of EVs is they can recycle energy when the driver brakes the car. This part of energy could be transformed to heat in conventional cars and wasted. However, fewer studies have empirically analyzed how many energies could be recovered in a trip in urban context. This study aims to analyze the recovered energy ratios of EVs in urban context based on the passively collected trajectory and the discharging or charging data from the EVs. The calculated recovered energy ratio will be analyzed from the following three aspects. The overall recovery energy ratio for all the trips and their temporal distribution and the spatial distribution. Here, we use two trajectory datasets which are collected from EVs in Shanghai. The dataset one has 20 EVs in 2015. It contains more than 1 million GPS points, which are collected every 10 seconds. Each point has its location, time step, battery information, the state of the charger, and the vehicle states. The dataset 2 has 25 EVs, which has more than 8 million GPS points. They has the similar features as the previous one, but it does not have the location information. Firstly, we combine the two datasets together and extract the trips according to the change of the vehicle states. Since here we need to capture the recycling process of the EV, so we need to guarantee the trip is long enough to contain the process. Thus, we remove the trips shorter than 10 minutes. And the two figures show the results, the distribution of the trip duration and the trip distance. We can see the most trips are less than 90 minutes and less than 20 kilometers. Then we calculate the recovered energy ratio for each trip. Since the trajectory cannot be recorded at any time, we can only calculate the discharging power and the recovered power as the sample points. So for the energy between two consecutive sample points, we just assume the power is linearly changed, and this figure from here to here. And the discharging or recovered energies are the integration of the power and the time, represented by the area of blue and orange here. So we can calculate the recovered energy ratio as the area of the orange and the sum of the areas of the orange and the blue. Here is the results. The results show that about 70% of energies could be recycled on average for a trip, but the recycle rates between different trips vary a lot. The standard deviation is about 11%. And these figures show the distribution and the cumulative distribution of the recover energy ratios for all the trips. It shows the recover energy ratios of most trips are less than 20 percentage. But it is also big enough from the recycling aspects. And according to the hour of the day, we grouped the trips into different hours and calculates the average recovery energy ratios of all the trips happening in different periods. And these figures for each box plot is represents the recovery energy ratios in each hour for 1 day. And we can see the recover energy ratio in the after the midnight are lower than those in the daytime, but the recover energy ratios in the daytime have no significant difference. And we further looked into the recover energy ratios in different urban areas. The basic idea is that the road network and the traffic conditions in different urban areas are different. And shown in the left figure, we divided the whole city into 4 subregions according to the ring road network of Shanghai. And the average of the recover energy ratio in the 4 areas, from the area 1 to the area 4. The average recover energy ratio are 11.8, 10.1, 10.5, and 10.8 percentage respectively. And we also adopt the t-test and the case test to examine the difference across different areas. As shown in this table, we can see the recovery energy ratios in the central area. That is the area 1, are higher than those in other areas. It is higher than area 2 and area 3. And the potential reason is that the central areas has more congested traffic situations and more intersections, which would result in more acceleration and deceleration events when the EVs run in the central area. But we didn't find the significant difference between the area 1, the central area, and the out area, because the area 4 is too big enough. So we think the variance is too big to capture its real recover energy ratio. In summary, the electric vehicles can recycle about 70% of the discharging energy on average in a trip. But the recover energy ratios of trips in different periods and urban context presents larger variance. And we also need to pay attention to the result in terms of the spatial distribution of the recover energy ratios. In our study, we only held 2 samples of trips that has the location information, so it is hard to get a robust conclusion from these points. And that's all from my side. Thank you for your attention, and thank you for your comments.
Okay, so thank you, Aoyong, for your presentation. It's regarding the energy saving ratio for based on Shanghai case study. As requested by the organizer, for all the Q&A session will be done by the chat box. For the audience, if you have any questions, and you can ask,
Sorry, Professor Xu, if I can jump in here. I think that would be a misunderstanding. It was just a recommendation. You can organize the session the way you want, no problem. the audience can speak their questions out directly. It's okay.
Okay, great.
Yeah.
Okay, thank you for your explanation, Lin Fei.
Yes, sorry for miss.
Okay, it's fine. So any question to Aoyong regarding this study from the audience? Aoyong, I have one question. You mentioned you want to categorize Shanghai city into 4 areas.
Any question?
On what basis you made this characterization?
Sorry, my internet is unstable. Could you speak again?
Okay, Aoyong, you in your one of your slides, you mentioned you divide the Shanghai into 4 areas, and on what basis you made this division, this subdivision for Shanghai city?
Excuse me, could you speak again? My internet is unstable.
Okay.
Could you repeat your question?
Yeah, probably it will be much easier if we use the chat box to ask questions.
Okay. I will see the chat box.
Okay. My question is regarding the subdivision.
Yes.
Of Shanghai city, and you divide the Shanghai city into 4 areas, 4 subzones. And on what basis you made this subdivision?
So your question is why I divided the whole Shanghai into 4 regions?
How did you divide? On what basis you made
okay.
this subdivision?
Shanghai has 3 ring road, the inner and the middle and the outer ring road. So we divide the whole city according to the 3 ring roads.
Oh, okay.
Yeah.
Okay. So that's quite straightforward.
Mm-hmm.
Okay.
And any other question?
Yeah. Any other questions for Aoyong? Just now you also mentioned about 70% regeneration rate for electrical vehicles in Shanghai as a whole. 70%. You get this data from your study, right?
Yes, this is from the study.
Okay, it's not a parameter from like a vehicle manufacturer.
No. I didn't get the actual results from some papers. But I get some results from the web page. They said according to their experience, it can sell about 50% can recycle 50% of energies when they drive the electronic car. So the 2 values are similar. And we also find the recover energy ratio got from the data in 2019 is higher than it's in 2015. So a possible reason is the technology of the car is developing in these years, so it can save more energies in the driving process or in the braking process.